Hello and welcome to the Microcart CrazyFlie controller integration walkthrough. This video will go over the integration of a controller and the data flow from sensors and set point inputs to motor actuation. So we'll start off with a little overview of the four key points that the data will kind of pass through. So we'll start with the commander. So the commander handles set points from the user or predetermined inputs or paths. Then there's the estimators. So the estimators will take data from the sensors and use it to infer and determine states as to where the drone is and its current rotation and things like that. Then you have the controller, which takes data from the commander, so the set points, and data from the estimators, as in the states, and it'll determine what changes it needs to make physically to adjust to reach those set points based off of its current state. And then there's also the power distribution. So that'll work on converting that data that's gotten from the controller to the PWM channels of the motors. So before we begin, we'll go over a couple helpful types, just so things make a little more sense when we discuss them later. So there's the control type. It contains roll, pitch, yaw, thrust. So kind of the three major axes and the thrust information for actually moving the drone. And so those are updated in the controller and then sent on to the power distribution to determine the power for each motor. Then we also have the set point. So the set point will be used to get information from the commander. So the commander will send all of this information to the controller, and the controller will take information from the state estimators, and they'll compare and determine what the error is, and then it can act accordingly. So the first thing that we'll go over is the commander. So the commander works on handling the set points. It receives set points from this CFlib, which communicates through the front end of the CF client that you may be familiar with interacting with, and that'll send set points. Or there's also this app layer that'll send set points, and these two blue arrows, those are the typical ways they go through. So that could be, Python script, or generally flying the drone to the client, anything like that. We'll talk about the high-level commander in the next slide, but it works in the same way. It'll send these set points to the commander, and then the commander will create a queue of the set points, keeping track of what time they come in. And then when the controller needs new set points, the commander will send those over. And it also works to kind of take out stale set points. So it determines, based off of a variable factor, how long it's had the set point for. And if it's past some sort of cutoff, then it'll just wipe the set point because now it's considered stale and it won't actually help with movement of the drone anymore. Here's an example of the commander communication protocol. So as you can see, there's 4 bytes for the 3 major axes of movement, and then there's also 2 bytes for thrust. So this is what's used to communicate over CFlib. This kind of packet is what you'd send. So now we'll go ahead and look at the code of what a commander would look like. So this is kind of the base commander module here. So as you can see, you have a set point queue, priority queues. So it sets up all these queues, and it will set these set points and get set points from the different things that we talked about earlier. And then, oh, sorry, I missed it right here. Here is where it kind of does that timeout that we talked about earlier. So if the set point is past the range that we don't think it's helpful anymore, we'll kind of cut it out, and it'll kind of disappear, and we won't use that anymore. So back to the slideshow, we will then cover the high-level commander. So as I said, the high-level commander works the same as the normal commander. It actually still sends data through the commander. But as you can see in this image down here, it has a little more steps that go behind it. So the CFlib, you can use that to send trajectories to the memory of the drone, and it will determine a path and from there the path will get sent back to the high-level commander and onto the commander. So this can be used to create like predetermined paths, save them onto the drone, and have the drone run them. And this can be used, the CFlib has commands for takeoff, land, go to XYZ coordinates, and stuff like that. So it'll use all of this information to update the set points. Speaking of the set points, we'll kind of give a little overview of what they look like. So there's each set point has two levels. It has a position, so XYZ, or an attitude. So that's pitch, roll, yaw, and each of set point also has different control modes. So it has an absolute mode, a velocity mode, or being disabled. So as you can see in this image down here, there's 4 major set points that are used to control the drone on a normal basis. There's the position control, velocity control, attitude control, and attitude rate control. And as you can see, here's their XYZ, so their position control level and their attitude control level. So obviously the position and velocity controls don't need attitude. And as you can see, they're set over here. So attitude is the actual attitude, and this is the rate of the attitude. So that's why you see that absolute velocity. And then you see that same relationship here between the position and velocity over here between these two. Now we'll kind of take a step into the stabilizer module, which is built up of estimators, the commander, and the controller. So the estimator works on pulling in the sensor data, as you can see here, and it determines its current state. The commander will get the set points from the things we communicated about earlier, and that'll go into the state controller. The state controller will then relay commands to power distribution, and the power distribution over PWM will communicate with the motors. So the stabilizer module is kind of these 3 right here. This works on stabilizing the actual output of the drone. So we'll start off with the first one, state estimation. So in a grand scheme of things, it obviously turns the signals that it gets from the sensors into state estimates. And that's incredibly important in determining where to move the drone, because you need to know where the drone currently is and need to know how much to adjust. So there's a couple of ways that the CrazyFlie can get information. So there's a gyroscope, accelerometers, there's time of flight, here's a bunch of float deck, some sweep angles, some motion captures, the lighthouse, which is the VR environment. All of those work to kind of integrate and take information in and create set points. As you can see here, this is kind of the base filter, the complementary filter. You have a gyroscope, accelerometers, and those work to create an attitude state and another attitude state in the Z-axis. And then there's the Kalman filter, which is way more in-depth. As you can see, it uses way more sensors, and it can determine attitude, roll rate, yaw, position XYZ, and velocity XYZ. So this can be used for a lot more automation and flight planning, with the fact that you get all of these different states. We'll kind of go over the complementary filter because it's a lot more easy to understand, and that's what the CrazyFlie uses in its base operation. So back to another code review, we will look at the state estimation. So this is there's a basic state estimator. So this uses a state type. We didn't cover that, but it stores, kind of the same as a set point. And as you can see, here we have a bunch of different measurement types that it pulls from. And then if we look at a specific estimator, so this is the complementary estimator. As you can see here, we're doing a gyroscope read, an accelerometer read, barometer read, the TOF read. So all of that is then used kind of back from the previous image that we looked at to then send to the controller, and it can make judgments from there. And then there's also, and a little bit more in depth, this is the Kalman controller. So kind of looking in the same spot, as you can see, the Kalman reads the sensor values a little differently, and we won't go into depth of kind of the model of how it reads those sensor values and determines helpful information from them. But as you can see, There's a lot more sensors it can read from here. Here's a TOF, absolute height, information with the flow deck, some yaw errors, sweep angles, all that other stuff, the barometric sensor. That's more in depth, but we won't need to cover that. And you can go into more in depth if you'd like back on the slideshow. If you see that link at the bottom, CrazyFlie provides models and examples of how all of the filters work and how the measurements are gotten from every device. So now we'll go into the next step, which is the controller integration. So the controller integration, it supports four levels of control. And we'll talk about the basic PID controller. Well, there are other controllers that you can incorporate, like an INDI controller or a Millinger controller. We won't speak to those exactly. So the four main controllers that you need to kind of work with is an attitude rate, an attitude absolute, velocity, and position. So these are also those set points that we looked at earlier, if they look familiar. And here's kind of the definition of a controller. So here's all the parameters it takes in. So there's that control type we looked at, the set point type we looked at, the state type that we talked about. You can get the sensor data if you wanted to perform more precise calculations and kind of determine error with more precision. So here's an example of the cascaded PID controller. We have the position PID that feeds into the velocity PID, that feeds into the attitude, that feeds into the attitude rate, and then that'll go onto the motors. So each PID kind of builds on itself and sends its desired position or desired state to the next one until you get the motor commands from the final PID. We won't go over exactly how the PID works, but we will take a look in the code at how the controllers actually interact. So if we look here, here is the base of the controller. So this is just like a base controller. Every controller operates under this. So as you can see, here's some of the other controllers that we talked about. And I believe for the CrazyFlie project, they've integrated their own controller that allows the students to program it in a way they'd want. So this could be changed at compile time. So you can force a controller to run on your drone at compile time. And then here's that controller definition that we looked at earlier with all those parameters that get passed in. And we'll look a little bit more in depth on just one of the controllers. So here's the attitude one. So as we can see, here's a roll output, pitch output, yaw output, and they get updated by this PID update. And the PID update is just a function that exists within a PID file that kind of just runs the basics of a PID loop and will give us the assigned output that we want for that specific axis of control. And then as you can see here, there's some more, there's desired values being set and some wrapping being done for yaw and stuff like that. So all the error will be calculated here and the output will get assigned to, in this scenario, temp variables. And then if we scroll down here, here's where it'll get assigned to those specific control variables that we looked at earlier. So that control type that stores the roll, pitch, yaw, and thrust, here's where that gets assigned. And just a quick look, kind of here's the PID. So here's that PID update function that we looked at just a minute ago. And as you can see, it kind of goes through, it calculates error based off of its measured value and its updated error, and then it will calculate what PID, based on what PID coefficient you're using, whether it's I or D, it'll calculate the corresponding components of that and give you an overall summation of your power to be sent to your device. Okay, now we'll go back to the slideshow and take a look at the next slide. So we'll kind of go over the motor control. So now that we've gotten our yaw, pitch, thrust, and roll, we can kind of determine what the thrust or the power assigned to each motor needs to be. So this gets handled in the back by FreeRTOS. So that's just the the program that's running on the drone, kind of calling all these functions in the back. You don't need to make any of these direct calls. They'll just get updated because this is a pointer here. So this function will always look at this pointer. So as you can see, you have your 4 different motors on the drone. And here's kind of your calculation of what the power will be. So, so you can see this motor uses pitch and yaw to determine roll and yaw, pitch and yaw, roll and yaw, and you can see the different calculations that are used to determine what the actual values are for each motor. And then it uses these and it adjusts for the battery voltage. That way, when the drone has a lower battery, it's not trying to use certain... It adjusts the power for the battery, so it's sets it to a percentage of voltage and not to an exact voltage level for the PWM waves. And we'll take a quick look at kind of that code and how it looks. So here is kind of the motor code, so we'll zoom in a little bit. So here's that code that we just looked at here. So you can see it pulls in these motor powers right here, and it assigns based off of those calculations that we looked at. And then here's where it's actually setting the power. So as you can see here, each motor is getting set to its assigned power, only when it's enabled, else set it to like a base idle thrust. And that's kind of all that's really done. Is there's no calls needed necessarily to specifically set the motor controls. It just uses this control pointer. So anytime you update that in your controller, it'll update in memory and it'll update here. So you don't have to do any advanced calls for that. So finally, we'll just do kind of a quick review. So we have the commanders. So as I said, they handle the set points. So we have just a normal commander, which will take set points from the CrazyFlie client or an application that you write in Python or whatever you just decide to have that be in. And then you also have the high-level commander, which works on predetermined paths that are then programmed to the drone. And those will capture set points, and the set points will have desired yaws, desired pitches, and desired rolls, also with the desired thrust. And that'll get sent to the commander, and the commander will send that to the controller in a queue. So that way, if you get a bunch in, you can store them up, and if they go stale, you can cut them out and bring in your newest set point. The next step is the estimators. So right here you have your estimators. That pulls data in from the sensors and gives you an estimated state onto what the current roll, pitch, yaw are of the drone. And then those will get passed with the set points from the commander down to the controller. And from there, the controller will determine the values needed to set for those 3 flight axes. So once again, roll, pitch, yaw. Those 3, it'll determine that from calculating error in the set points and the current state. So it'll figure out how far off it is and adjust to how far it needs to go. And then from there, those values are then sent to the motor power distribution segment that will then generate the PWM waves to actually control the motors. And that would be it for the overview of the controller integration. There's other videos on the CrazyFlie on the Microcart YouTube page. Go ahead and look at those. There's another video that explains more in depth on the integration of the stabilizer, more specifically a PID controller. That new PID controller that I was talking about that they added called Student. So that'll give you kind of the idea of how to integrate your own PID controller and how to integrate with these different segments like the commander, the estimator, and sending it to the motor.